Did you know that a conservative vector field is like a well-behaved child? It doesn't matter what route it takes, it always ends up with the same result, just like a child who always comes home for dinner, no matter where they've been playing. In the vast universe of vector calculus, conservative vector fields are the good kids on the block. They're neat, they're predictable, and they play by the rules. A conservative vector field, you see, is essentially a vector field that is the gradient of some function. This signifies that irrespective of the path chosen between any 2 points in the domain of the vector field, the line integral remains unchanged. This fascinating trait of conservative vector fields, their path independence, is like a homing beacon. No matter how convoluted the route, the outcome remains the same. Whether you take the scenic route or the expressway, the result is independent of the path chosen. It's based solely on the starting and ending points. Another captivating aspect is their irrotational nature. The curl of a conservative vector field is zero. In simpler terms, it implies that these vector fields do not exhibit any rotational effect. They're like well-trained ballet dancers performing in perfect synchronization, each step gracefully transitioning into the next, without any whirls or twirls. Furthermore, these vector fields can be represented as the gradient of a scalar field. This means there's a scalar field out there for each conservative vector field, which when differentiated produces our vector field. It's like a parent-child relationship, one giving rise to the other. Now, these conservative vector fields aren't just fascinating mathematical constructs. They have serious real-world applications. They're used extensively in physics and engineering. They help calculate the work done by forces, design electric motors, and model fluid flow. Consider the gravitational field, the electric field of a point charge, or the magnetic field of a straight current-carrying wire. All these are examples of conservative vector fields, silently working behind the scenes, driving the physical world as we know it. In summary, conservative vector fields are the well-behaved children of the vector calculus world. Their key traits include their path independence, their irrotational nature, and their ability to be represented as the gradient of a scalar field. These properties make them an invaluable tool in many fields, particularly physics and engineering. So next time you come across a conservative vector field, remember, it's just a good kid, playing by the rules.